We cherish the international cooperation. We think it's needed. We know that we cannot do everything on our own, not even in Europe with our 28 countries. We cannot do everything. So we do want to work together with everybody else, and with that also learn from what the others are doing.
Welcome to Manage This, the podcast by project managers for project managers. I'm Wendy Grounds, and with me in the studio today is Bill Yates.
Wendy, we're going to go to space today. Let's do it.
I am so excited about today's guest. We get to sit down with a project manager in human and robotic exploration at the European Space Agency. And this is Philippe Schoonejans. Philippe is in the Amsterdam area of the Netherlands, and we're very excited to have him with us today. We're particularly going to talk about the politically complex international environment that he works in with many stakeholders and many countries. The European Space Agency, I think he said, has 28 member states, and they also work with other countries around the world, including NASA. He'll tell us a little bit more about that. But some of the projects that Philippe has worked on, he's been the project manager for the European robotic arm for the International Space Station, as well as working on a sample transfer arm. He's the project manager and team lead for that. It's for a Mars Sample Return mission.
Isn't that fascinating? And for our listeners, you're going to hear a lot of abbreviations or acronyms. So ISS, ESA, International Space Station, European Space Agency, different things like that, NASA. But Mars, we have been trying to get to that red planet since 1960. We've been attempting to put satellites orbiting around that planet. And there's been some success, but the one thing that we've never done is bring anything back. We've had pictures, we've had digital data, but we don't have any actual rocks or samples. And so this mission's going on now. We do have, I think since 2003, the ESA has successfully put rovers on Mars. And so they're slowly moving across that little red planet and collecting data. But one of the fascinating things is Philippe and his team, they're working at bringing the rocks and the other things that they can collect back to Earth. We haven't done that yet.
It's easy to get overwhelmed just by the vast scope of this project and the incredible things they're doing. But we're going to find that Philippe has some really good information and really practical advice for project managers, particularly those who are working in an international community. Let's get right on and talk to Philippe.
Yeah.
Philippe, welcome to Manage This. Thank you so much for being with us today.
My pleasure, entirely.
I want to ask you about your career path. Could you tell us, have you always been interested in space and how you got to where you are today?
Well, I think maybe I was not the little kid who was always already toying around with rockets in the garden, but I did have a board game, which I liked very much. It was called Space Race. It was about space mining, and you had to throw a dice and get your rockets to various orbits and get it into the moon. And I loved it, but there was also a bit of frustration because my brother convinced me to buy this game together, and I had to empty all my savings, and then we played it, and he only played it just once, and then he got fed up with it. And later he went into languages, so I emptied all of my little kid's savings to buy this game, and then I had to find new friends to play it with. But maybe it's out of that frustration that I ended up in space technology.
Yeah, you had an early investment in space, so you had to, as a small child, you had to just commit to it.
And that was 100% investment. So there was, in fact, a relatively very large investment. But now later, I did my studies in nuclear physics. Some people say that the parallel was there that I worked with large particle accelerators. So there was already some fascination for things which have a little bit of grandiose element in there. So I loved that absolutely. But when I'd finished, I applied for a space company. It was Fokker, it was an aircraft company. They made airplanes, but they also had a space division. But I also, to be honest, I applied at Shell and I applied at Siemens and at Philips Electronics to be a chip designer. So that I had choice in the end of 3-4 jobs, but I think the space fascination won. And when I was doing that for 5 years, our colleagues of the European Space Agency who were at that time our customer. They asked me whether I would not want to come and join them. And I absolutely loved that. And I've loved it ever since. It's such a fascinating and inspiring international environment.
Let me ask a quick follow-up question just to help those that are in the United States or maybe in North America that are listening. Compare NASA with the ESA.
Yeah, it's quite different. I think the biggest difference is that ESA has like 28 member states. So we are representing the interests of all of these member states and not just one like in NASA. So it's very democratic, so very, very political. And it's political to the sense that each participating country wants to get back what they put in. So that also means that the bigger countries make bigger contributions. They have a more important vote in most cases than the smaller countries. So that is for sure a complication in ESA, but it's also very inspirational.
What is your role at ESA?
Today, I'm a project manager in the Mars Sample Return mission. And that's particularly interesting, I think, for the Americans, because it is a joint mission between NASA and ESA. And it requires 8 space systems to work together in concert to get Mars material back to Earth, which is something which has never been done before. And ESA has 3 contributions to this mission, and I'm the project manager of one of them. But with that, I'm also very much involved in the discussions on the overall missions and the discussions between ESA and NASA. In addition to that, I've been doing a lot of technology stuff in ESA. For a long time, I was the chair of the forum that decides on which technologies get the budget to be developed. And so it comes from the needs of the missions that we are planning. So where do we have a gap in technology? What is it that we still cannot do and what is very risky? And let's focus our research money on those. So sometimes it's a short-term thing, but usually it's a long-term thing. Like we are not yet good enough in rocket engine of such and such type, which maybe we need for future missions. Let's initiate a 5 to 10 year development to get that going. And then, of course, that was a tricky job because there were always way more proposals than we could afford. So that was very, very interesting. I've also worked on standardization of space technology. So we have lots of space standards that we use for all of our developments. And we had to decide, okay, in which direction should they evolve? Which ones are we still missing? How do they relate to the standards that other agencies have? In the end, it's very, very important because in all the international cooperation, we typically want to work according to our own standards. And the others do, like the Russians would work to Russian standards and the Americans to the NASA standard, the Japanese to the Japanese standards. And we have to declare that they're all equivalent. But also sometimes you have to convince the partnering agencies that they are actually equivalent. Otherwise, they would end up asking us, can you please work to the NASA standards? And then all of our industry has to change the way they do business. So this is an important subject, which I enjoyed very much. But I think where my heart is in the operational part, like really run a project.
Philip, looking back on your long career with the European Space Agency, what are some of your favorite projects or those that you're most proud of?
Well, I think the moon one that I just got out of was very, very difficult because it was about defining a moon space station that is going to fly in 2024. So it's short term, that the cooperation with Russia, Japan, Canada, Europe and US. It was very, very, very international. And now we got to the point that we managed to also convince within Europe all of our member states that they're okay to put money in it. The multifaceted aspect of it was just enormous. But the other one, which is very, very close to my heart, is the European robotic arm. It's like a 12-meter long manipulator that has to go to the ISS. And it's been a nightmare, actually, because the thing has been finished years ago. And then our Russian colleagues have had to delay the launch maybe 10 times by 1 year. One time, 10 years, that would have been easy. Then we would have simply put everything in storage and we take it out of storage 10 years later. But it was 10 times 1 year. And now finally it's going on May 1st next year. So that thing is coming back and it is still very, very dear to my heart. I've worked on it forever. I know everything about it. It was my first project when I came to ESA. And I'm still very dedicated to get that in orbit. I think those two qualify for my favorites.
Yeah, the robotic arm, so that's going to be on the International Space Station, is that correct? Is that where
Yes.
it'll be implemented?
On the Russian part of the International Space Station. So on the US part, there's a Canadian robot arm. And on the Russian part, there will be a European robot arm. And also should be able to hand over boxes to each other. So they should be able to cooperate. But there's been a lot of discussion on whether we needed 2 robot arms on that one space station, or whether it would be possible for one robot arm to walk over to the other one, to the other half of the station. The fact that there is a Russian half and an American half is already something special, but it works. All sorts of technical and political aspects to it.
Just a query, what exactly does the robot arm do? What would its functions be?
First, it will help install some equipment on a new Russian module that is flying next year to the ISS, a research module. And this thing needs radiators to get rid of its heat. The radiators are already stored on the ISS, but they are very, very large. And they have to be taken out of the storage there and connected to this Russian module. They are too big to handle by astronauts during a spacewalk, so you need a robot arm to do it. Our next step is to place on that same module an equipment or science equipment airlock, something which allows them to bring scientific equipment from inside to outside without always having to do a spacewalk. So basically you place it in the airlock, then the door closes on one side, it opens on the other side, a robot takes it out again and places it wherever it needs to be done. So that's something where the ERA arm first has to connect this airlock to that Russian module. And that's an even bigger volume and mass to be operated. And then once that thing is there, it has to operate it and place the payloads outside. So that is our, if you want, our killer application for which where the Russian segment cannot do without.
Philip, you brought something up and I was going to ask later, but I'll go ahead and ask it now. I did some reading on some of the work you guys have done with that gateway, that airlock. And it was fascinating to me to think about the challenges that you have because, again, you're trying to think about how this equipment and this technology is going to work in space. It's just hard to mimic that. But you guys came up with a clever way to mimic that weightlessness and some of the constraints that you have in space while not going to space. You know, you did some things underwater and did some prototyping. Talk about some of the advantages that came out of that approach of prototyping.
Yeah, I think typically we would try to prototype everything and test everything before, but of course we have no anti-gravity device.
Yes.
That is the biggest hurdle that we have. So if we would design everything that it works on Earth, it would become typically too heavy to launch to space because it needs to be able to support its own weight. In space, it does not have to support its own weight. So what we want to do is we want to make it lighter. But then if it's lighter, then you cannot test it on Earth. So we have to find ways to be able to test it on Earth, even though it cannot support its own weight. So we have 2 methods for it. One is that we would have systems that go on air bearings. So we have a very, very flat floor. We have a little trolley that floats on this floor by an air cushion, like these devices that you can have, like the games that you can play on air
Yeah,
cushion.
like an air hockey game.
And
yeah.
then it's almost frictionless. It's an air hockey thing. Actually.
Yes.
And then it's almost frictionless. So you can, in one plane, you can have, if you want, a frictionless motion, which in that plane is equivalent to having no gravity. Of course, you cannot have a 3-dimensional operation because once you go up or down, then it would no longer work. But we can also use that system to qualify and verify our simulators. So the simulators then are calibrated against operation on that flat floor with the air bearings, and then you can make a 3D simulation in big computers, and with that you can verify whether your system will work. So that's one method. The other method is exactly what you mentioned. We can go underwater and then have flotation elements connected to it and little lead weights, and you can, if you balance them, you can make it such that your system is exactly floating in the water. And that's the same that's used to train astronauts for their spacewalks.
Yes.
But we also have, of our robot arm, we have full-size, 12.5 meter long robot, which is qualified for working underwater. Can be exactly neutrally balanced so that it's as if the thing is weightless. And with that, we can use it for training and for verification of our operations.
You've told us about your past projects. What are you currently working on? I know you've worked on some moon projects and you're working on Mars projects. So where's your focus right now?
Yeah, I have the tail end of this ISS project with the European Robotic Arm, which I just explained. And I hope to be able to do that with maybe like 20% of my time. But the bulk, then the other 80%, is for the Mars project, working on this famous Mars Sample Return mission, where there's a lot of excitement couple of weeks ago when this Mars 2020 or Perseverance rover was launched to Mars. And that is a key element in that mission. And it is very important to us because that rover will collect the samples of Mars material that in the end our ESA systems will have to get back to Earth. That's my focus now, and I'm working on that since the 1st of July. So I'm very fresh. It was very interesting here in the Netherlands that the media found out within a couple of days that I was doing that, and they wanted me to comment the next morning at 7 a.m. on the radio about this mission. So, guys, I know nothing about it yet. I'm only doing this for 6 days, but on the next mission, like in 2 weeks from now, I will assure you that I'll be an expert in the meantime, and then I can do it. So I'm on a very steep learning curve here about what Mars is and what the atmosphere of Mars is, what is the orbit, why you can only go there once every 2 years. So now I'm getting into it, and I would probably say I'm up to speed now. It's very fascinating.
If we launch a rocket today and our target is Mars, how long will it take for us to get to Mars?
Yeah, it depends a bit, but let's say 8 months.
Okay.
The Perseverance rover will be there in about 8 months, the end of February. It depends a bit on what method of propulsion you would use, whether it's with electrical or with the chemical rocket fuel, or whether you make use of the gravity of the Earth and Moon and Mars. And it depends on whether you go with people or not, and how much mass you have. But typically, it's like 8 months. For people, that's very difficult because they've done also an experiment which was called Mars 500, where they stuck 6 astronauts in a simulated Mars capsule for 500 days, which would represent a return trip to Mars. And they wanted to know what that was like, and whether they would kill each other, whether they would be happily getting along with each other. And they found out a couple of very interesting things. That, for instance, boredom was one of the biggest enemies.
Yes.
The daily meal was getting very, very important. So there was, of course, from the food that they had taken, some food was, let's say, more appreciated than other food. And of course, it was always the same people who would take what was generally regarded as the best food, and that would create some irritation. Like everything you have in normal life would be amplified because you're stuck with 6 people in a box that you cannot get out of.
Can't imagine. Yeah.
It was a very, very valuable thing because it is seen as something that we have to somehow master. And also the training concept has to change. If we go for a short mission to the International Space Station, we teach the astronaut everything they need to know before they go. And when they go there, they can immediately apply it. For a Mars mission, there's 2 differences. One is that you only arrive like maybe up to a year later than when you've trained. So you've forgotten a lot. And you have, for that whole year of the travel to Mars, you have absolutely nothing to do. So better to use that year for training. So better to beam the online courses to your Mars capsule and do the training while you are there, apart from maybe some things that need physical access to hardware or whatever. So the whole training concept had to be rethought. So it's really not a simple thing to get people to Mars. So the current state of the art is getting people to the moon and getting robots to Mars. And maybe the next thing in 20 years from now is getting people to Mars, which is our holy grail.
So the moon is really a training ground for getting to Mars?
Absolutely. And I think for the US, that was for a long time, that was really the only goal. So I think in the US, when we started to revive the moon program, of course, the moon program was done 50 years ago, but the next generation, it was like a proving ground for going to Mars because you could test all of these technologies, all what you need to know if you're in deep space and you have to face with radiation or to couple rockets to each other. So all of this was better to do it near the moon where you can be back in a couple of days. And that purpose is definitely still there for everybody. But there was also, especially with Russia and ESA, there was also the goal of the science of the moon itself. Now, I think also in the US this has changed, that they're also very, very interested to get to the moon and to do the moon science and to get people on the moon. And that's also why Mike Pence stated that he wanted to have in 2024 the next man and the first woman on the surface of the moon. And that gave a lot of push to that moon program.
Philip, I'm curious, has COVID-19 and this pandemic, has it impacted the work that you've been doing on these projects?
Yes, very heavily. It's difficult. We have had one case where there was a Mars rover that was planned to be launched this summer. It was called ExoMars. It was a European rover full of scientific equipment. And we had to postpone the launch because we couldn't complete all of the testing, because all of the engineers who have to travel around in Europe and Russia to perform the test, they were all faced with quarantine restrictions or restriction to even go at all. And everybody's incredibly worried about the COVID thing. So we couldn't finish it. And the launch window is only like 1 month that the position of the Earth and Mars is good enough to get there. Basically when they're on the same side of the sun. If one is on one side of the sun, the other one on the other side of the sun, it's way too far. You cannot possibly reach it. So in that launch window, we could not manage. So that means that the thing had to be postponed by 2 years. And that costs, of course, millions. That's incredibly expensive. The other thing that I'm now facing is that for this launch of our European robotic arm in May next year, we have to go testing and doing the launch integration in the Russian launch base in Kazakhstan, the Baikonur Cosmodrome. And we were invited to go there this September. And our medical services recommended very, very strongly against it. And that was one thing. And the other thing, it would imply like 6 weeks of quarantine, like 3 times 2 weeks. You go via Russia. So 2 weeks after we leave Moscow to get into Kazakhstan, 2 weeks in Kazakhstan before we would be allowed on the Cosmodrome launch base, and then 2 weeks when we would get back in the Netherlands. And that all of that for a 3-week test. So that was very prohibitive. In fact, just an hour ago, I had a meeting with the medical center again, because the launch has been now put a little bit earlier, so it's getting more urgent. So now we are trying to switch modes and look at, okay, what can we do to make it happen? Rather than the easy way, say, well, can I do it? What would have to happen to do it? So we're looking at possible charter flights and being exempt from quarantine thing with special permissions and lots of paperwork. And we don't yet know whether we will succeed, but it's a project in itself to get our engineers to Kazakhstan to do the necessary testing. And I think efforts like this are all over the place. I was quite impressed with the fact that NASA and the Jet Propulsion Lab managed to get this Perseverance rover within the time window to Mars. And apparently it took also a lot of special effort to maintain that schedule in spite of COVID-19 virus.
Philip, this brings about a follow-up question with me. I'm just thinking of you as a leader of a team. You guys are facing delays. You have technology-related delays. You mentioned the project that keeps getting pushed back a year, the robotic arm. Now you have COVID-19, you have a worldwide pandemic. How do you keep your team motivated when there are frustrating elements like this that are just a part of, well, some of it is a part of the business that you're doing, the technology delays, but then some are pandemics that nobody would have predicted. How do you keep your team motivated?
Well, I think we are incredibly fortunate that all of this space work has this immense wow factor.
Yes.
There's a lot of self-motivation. So we have basically never any problem to get staffing. When people are there, they're very, very, very dedicated. It is still fascinating. Of course, the Corona thing is frustrating. So that's new. But to be honest, I've been very amazed in this long delay period that people were still so motivated to do a good job on that. And that's also still, we were able to get some young, new people to work on a project which has been running forever, which has had some delays. But we are in constant upgrade and improvement. Basically, our ground stations, for mission control station on ground, has been upgraded a couple of times because the computers got old and therefore there were no longer any spares, and therefore we had to upgrade them. And then we had to also upgrade the application software which ran on them. And in the meantime, therefore, we improve on it and we made better software models and better visualization in our simulators. And apparently that's still incredibly fascinating for people to work on. So we don't have to do anything special for it. We don't have to give them any goodies. No pay rises have to be done before it. No, there's an incredible motivation all along.
Yeah. There are folks just like you, I'm sure, that are wired, that have a love for space and the adventure of it and are just delighted to be a part of this mission. So that's, as a project manager, you're in a unique space there. And that's great to have a team that's motivated and thrilled to be a part of that mission.
Yes, I think the only drawback that you can take from it, maybe, that nobody ever leaves ESA. So So that means that you don't have all the time that your boss is leaving, and therefore you have lots of opportunities to move up.
Yeah.
That's maybe, if you want to look for a drawback, that is the drawback. On the other hand, it also means that there's very good continuity, and there's a lot of knowledge stored in the brains of people. And I think we get better and better in writing that down and looking at our lessons learned. And basically the knowledge management is getting really important. And it is also, we see it important because we've seen some difficulties with our colleagues in Russia during the times of the perestroika and glasnost, that there are a lot of very, very clever engineers in working in space, that they had an opportunity to work like doing payroll programming for a foreign bank in Moscow or whatever. And then they would make so much more money that they would leave. So they've had a period where there were many people leaving. Also, there are a lot of mouth-to-mouth handover of experience from the very old engineers. So in the end, there was like a generation that was underrepresented. Like you had the old guys who were working on the docking systems and the Apollo-Soyuz missions in the beginning. And then you had the new guys who were still very thrilled with the space technology, but the middle portion was underrepresented. Some people attributed some of the trouble that they had to that. So we are keen to still do very much our knowledge management to make sure that we still conserve all of that. But typically we don't have this problem of people leaving. So that's a very good thing to have.
Philippe, you've worked with many agencies, many countries, and we'd like to just hear a bit more about this, the political dimension of your project. Which other space agencies do you collaborate with? You've mentioned Russia. What are the others? And does every country do their own thing? How do you collaborate?
Well, I think on several of these mega projects that are simply too big for any one agency to run, like the International Space Station or this Mars Sample Return mission, typically it's a cooperation where each agency provides some elements and they are then basically connected to each other. Almost always this is done without any exchange of funds. So we are not paying the Americans to build something for us. The Americans are paying something to us to build something for them. Basically, we build something, they build something, and then we hook it up together. So that also has the advantage that the European money or the money funded by the European member states stays in Europe because it's used to pay European companies to develop a system. And the same in every country. And so we do that typically with Russia, Japan, NASA, and Canada. I think those are our most active partners. And with those also we are used to making these big memoranda of understanding where we describe exactly which contribution is done by which partner and how in the end they are connected to make one giant mission. So if you look at the ISS, there are drawings of it where there's a color scheme stating from which country every module is coming. And then that's the whole rainbow of all of the contributions that have been hooked up to each other. And what you need is a standardization of the docking connectors so that is possible. You need to know on which launcher you can go. And I think there's maybe one little disruption was when NASA stopped the space shuttle program. And then there was only the Soyuz left to actually fly astronauts there. So that was a difficult period for everybody because there was then a very, very strong reliance on Russia, which was okay because they turned out to be reliable and the Soyuz kept flying and there was never any casualty, but it was still seen as a risk. So now it's good that we now with SpaceX, we have now a second way to get to the ISS. But typically that's the way to do it. And then we are still left with some cultural differences and differences in the funding schemes in the various agencies.
Philip, this just screams at me because if I see the incredible challenges, the science and technology challenges that you guys have tackled and overcome, just taking the ISS, the International Space Station, as an example, it's different organizations from different countries with different members and different budgets, but you guys have figured it out and you've got this cohesive station that is usable and providing amazing information and data for the world, and science is better because of it. So to me, I think of project managers who complain because they have all these different contracts with different companies that are maybe vendors on the project that they're overseeing. It just makes me laugh because I'm one of those guys. I've complained about these, these contractors, these vendors, they don't get it. We're saying one thing to the customer and then we're showing them something different, or we're having this blunder of communication where we're not sure who's going to do what. So these memorandums of understanding, that's a great way to do that. And obviously, there's just a community that's passionate about the goal. In this case, the space station, which is usable and all the countries can contribute and then gain from it. Share your advice with some of those project managers like me who are struggling with other relationships, vendors, and other stakeholders. What are some of the ways that you guys have been able to see success break through when you think, okay, we can't communicate? How can we be clear on this?
I think we put a lot of focus and a lot of effort. In fact, I think probably most or all of the project managers in ESA have been doing this, have gone also to a course that was given in Kennedy Space Center in Florida with participants from, let's say, all over the world about cross-cultural project management. And we've spent a lot of time there to explain to each other what also our funding process is, which turns out to be very, very important. Like you have a yearly budget assignment at the end of the fiscal year, or the start of the fiscal year, somewhere in October. Every 3 years, we have our European ministers who are responsible for space. They get together and then they assign the money for 3 years. So there's completely different timing. In Japan and Russia, it works again different. So it already starts with the fact that when we want to start such a very large endeavor, that everybody's timing is different. And we all have different moments that we need to have a certain level of definition. Otherwise, we cannot convince those who have to fund us that this is going somewhere. And that could mean that we need to know exactly what are the interfaces of our system and to what it can be connected in which way. And we asked this to some other engineers, but we have not even started to think about that. That only in 2 years we need that. Our engineers are not working with it. Today we have different priorities.
Yeah.
So that's already very difficult. Then you have things in the way every country works. And we have been grilled with all of that type of information, with research which shown the differences in how people communicate. What is the power distance? Where is it more hierarchical? Where is it might be a more flat organization? Indeed, we've seen all of the stereotypes that they actually have a basis. Like the Japanese never say no, but if they say yes in a certain way, then it can take forever before you actually get the information.
Yeah.
So maybe this was not so strong yes in the first place. I think the Russians have usually good strategy that they try things many times and then every time they get better.
Yeah.
And we have more the thing that we want to run simulations and computer programs and figure everything out before we even start cutting any metal. So there's a different pace in there. And as long as you're aware of all of that, there's usually a way around it. And we also have the teams that are working together. We try to keep them. So the people who are working now on this Lunar Gateway space station that has to orbit the moon are the same that are all coming from the ISS world. So they have the experience on how to do this. We reused also the experience with setting up a legal framework for all of the international agreements that have to be signed up and that have to stand up to whatever arbitration could be needed if there's ever a conflict. So there's tons of lawyers involved in exactly how to write all of that down. So you don't want to reinvent the wheel every time. That is difficult. So I think as long as this cooperation is started, we cherish it and we try to keep, with the same partners, try to keep the good work going. Very often when I give presentation indicating all of the differences that we have with cross-cultural differences, then I end my talk with a picture of the space station saying, in spite of all of what I've told you in the last half hour or hour, we actually do get things done.
Right.
Still, indeed, it's a miracle. It's also the result of hard work. So some people say that aspect of it and the political aspect and the cross-cultural aspect or the cooperation is in principle at least equally, if not more difficult than the technical part of it. Because believe it or not, space is relatively a conservative area of engineering. We try to use what we know works. There are some areas where we have to develop something new because nobody else will invent for us how you can make a system that works in the dust storms of Mars and with the extreme temperature differences that you have there. So that is certainly something that we have to look at. We have to look at the material science for all of that. But if we look at software or image processing or vision software in other areas of technology, there's way more billions being spent. There's all of that effort put in image recognition. We are not going to try and top that. We use whatever we get out of other areas. So we have a lot of spin in addition to the spin out that we have from space technology.
Right. That is fascinating. Philip, you shared so many great takeaways to me as a project manager when you're dealing with diverse agencies, we'll say. You talked about proximity. It was important for you guys to all build a relationship by being close to each other. And then understanding, you talked about your organization needs to understand NASA's timing and NASA's budget, and Japan and Russia's timing and their budget, because they're different. So if everybody has a deep appreciation for that, if I know what makes this contractor look successful, then I can better adopt my plans around that and make that happen. And then you guys all had a common mission too. At the end of the day, you want to have this space station, which is completely functional, and the scientists that are on it can go across from one section to the other without a passport. They can go from Russia to ESA to NASA to Japan and have the continuity of technology and be able to get the job done while they're up there. So there's that common mission that I think you guys have done a phenomenal job of keeping right there at the top. That's the flag that everybody's looking to and pressing on towards. So those are great takeaways for our project managers, and some that I would call less complicated, perhaps less complex projects that we manage.
But also, therefore, they take long. Huh?
Yes, they do. Right.
That's something that we all have to realize, that it can take forever. Project can take 10, 20 years easily. But maybe it's also like any big infrastructural project. Elsewhere, you have bridges or metro lines to be built under medieval cities. I think there's other big infrastructural things that take long, but definitely in space it takes long. But if you get all of these countries together, there have been some people have been saying, when we were thinking about what is our motto for space exploration, it has been brought up that maybe the space exploration would help also in keeping peace, because then you have all of these clever engineers that are all working together rather than inventing weapon systems to beat each other. But in the end, we never put that in the motto because it was a bit too grandiose. But there was a point to it. And in effect, we have in the discussions, especially with US, but it plays a bit of a role everywhere. We have also a lot of discussion on export control of high-tech knowledge, because that is something really that is haunting us big time. That happens so often that we need to exchange some data, which we need for our engineering, but it first has to be cleared, in your case, by the Department of Defense, or in our case, by a board that represents all agencies. We have also export control for things leaving the European member states. We have had some difficulties to exchange information freely between the different agencies because of the export control regulations on key high-tech technology, which could be used for military purposes. Almost all of what we do could possibly be used for military purposes. And that's been really hard, especially if we have not yet been able for a large project to organize exemptions, organize, let's say, a mode in which we can more freely exchange that information. That sometimes we need the data, but it's still classified, and we have to wait until that has passed the scrutiny of whatever agency or organization or people have to look at it. It's a practical hurdle that we have to pass, and in the beginning of a project, it's difficult and time-consuming. So I think it's just one of the practical issues that make the international cooperation difficult. And once we have it behind us, okay, it typically works, and we are proud that we managed to do something big together, but it's not so easy.
Philip, I want to ask a practical question. You are a nuclear physicist, and you work with brilliant scientists, not just in Amsterdam, but all over the world. How do brilliant scientists figure out the right way to communicate with people like me, or perhaps politicians or other people who have the money or the resources that you need, or just are able to influence your project? How do you dumb things down so that people like me can understand it?
Yeah, I think to select among the clever engineers, to also select and look at the ones that are better at dumbing things down than others.
Yes.
Because we still have the people who are the big wizards with the hair looking like Beethoven and are incredibly clever, and we absolutely need those. But some of them can also be a bit difficult, or they are not always super able to explain. But there's also others who are much better at explaining and maybe not as good in the details as the other people I just mentioned. So we absolutely need both types of people, especially for two areas. For the media is important, but it's even more important for the funding bodies, that we explain why we do what we do and why it is important, and why something is really needed or not, especially if you get into a mode where there have been some serious setbacks and we have run out of money and want to go back to the member states and can you please put some more? And the first question, okay, great, why? We already given you the money. And then you also have to explain maybe sometimes complex technical problems that have appeared, which you rather not have, but on the other hand, we almost always do something which nobody's ever done before. So you also cannot completely rule out that you would ever run into a serious technical problem.
Any final advice, inspiration, lessons learned? Any last words that you'd like to leave for our audience?
I just would want to finish with the fact that we cherish the international cooperation. We think it's needed. We know that we cannot do everything on our own, not even in Europe with our 28 countries. We cannot do everything. So we do want to work together with everybody else, and with that also learn from what the others are doing. We have a lot of clever people who would want to have the most beautiful engineering solution for everything. I could myself easily also fall into that trap because I see beauty in a very simple design, but simple is difficult. And I think we should also accept that the better is the enemy of the adequate, and that we have a lot of political constraints where we cannot always take the best company for each particular job because we have to develop high tech in all of our member states. So there's a good push that we also spend money in all of those member states because the reason that they fund ESA is because they want to develop their own country in terms of high tech. So we have a lot of new countries that are just starting, and everybody has to have a share into all of this. And sometimes this leads to a solution which is completely adequate, but not the 100% perfect solution. So I think our job is to be happy with that, and within the full set of requirements that we have, which are technical, but also political and financial and timing-wise, we have to come up with the adequate solution. And when we found that, we should be happy with it and proud of it. And it is an important thing for us, which should give us the job satisfaction. And I think for most people that works. That's one thing. The other thing maybe that there's been a lot of debate in my field on humans versus robots and what is better to use. And I think we should get out of that. We have to have cooperations with humans and robots. There's a lot of tasks which are either very boring or very repetitive or dangerous, and they could be done by robots, but we also cannot do without the creativity and the on-the-spot problem-solving capabilities of people. So, again, that is something where we need both, and some cooperative scenario is always my favorite. I think that's another thing for which I would want to have a plea.
Just the enormity of what you guys are trying to accomplish, and then the constraints that you have and the relationships that you have to manage. My hat's off to you. Congratulations on the work that you guys are doing. And I think we can all learn from some of the lessons that you guys are playing out day by day. So thank you.
Well, pleasure.
Yeah, we've really enjoyed talking with you. Thank you for your time. And it's been an honor. It's been really a joy to hear what you guys are doing and to have another perspective. We've had NASA scientists talk to us before, but I've always been interested in, what is happening in ESA and other parts of the world. So I really appreciate your input and what you guys are doing.
Okay, well, next step for you to interview a Japanese and a Russian and see another,
telling you, I'm working on
possibly
it.
very different perspective.
Yes, that's it. That's perfect. Yes.
Yeah,
All
we'll
right.
head off to one of those two next.
Yeah.
Philip, thank you so much. We really appreciate your time and are so blown away by the challenges that you guys are tackling and the success that you're having. So thank you. Keep up the great work, and let's get to Mars.
Yeah, lovely. Couple of years, and we'll be there.
Awesome.
Hey, thanks for the chat. It was
All
very
right.
nice.
Thank you for joining us this week on Manage This. If you found value in this episode, we'd appreciate a rating on iTunes or a comment on our website or wherever you listen to the podcast. You've also just earned some professional development units. To claim your free PDUs, go to velociteach.com. Choose Manage This podcast from the top of the page. Click the button that says Claim PDUs and click through the steps. That's all for this episode. Until next time, keep calm and manage this.